Welcome. In this video we shall study the use of double sampling in ratio estimator. Now what happens in our usual ratio estimator, we have the ratio estimator for estimating the population mean is y bar equal to small y bar by small x bar into capital X bar. So where we take the population mean for the auxiliary variable x bar is known to us in advance. So but it happens that population mean x bar is not known, and in this case the ratio estimator of estimating the population ratio or the population mean cannot be used. So the usual procedure in such a situation is the use of the technique known as the two-phase sampling or double sampling procedure. So the technique consists of following two phases. One, draw a large preliminary sample of size n dash from the population and measure only the auxiliary variable x, so that we can calculate x bar dash, the mean of this sample, which provides an unbiased estimator of the population mean x bar. So that is expectation of x bar dash equal to x bar. So this preliminary sample is selected to estimate the mean of the auxiliary variable. So this sample of size n dash is called as the first phase sample. Now the second, draw a random sample of size n from the population to measure both y and x. N is less than n dash. So here from this sample size n, we measure both study variable and the auxiliary variable, and y bar dash, y bar and x bar be the sample means of the study variable and the auxiliary variable for this second phase sample n. This is our population of n units. Suppose we draw a sample of size n dash and calculate x bar dash. So this is called as the first phase sample. Again we draw a sample of size n, observe both y and x and calculate means y bar and x bar, for this is known as the second phase. Now the second phase sample of size n can be drawn from this first phase sample, and also it can be drawn directly from the population. So here two cases arise. The second phase sample is selected from the first phase sample of size n dash, or it can be selected independently from the population again. So here in this video we shall consider when the sample size n is selected from the first phase sample n dash, and in the similar way we can consider the second case where n is selected from the population directly. So we shall consider the case 1 only. The second phase sample of size n is selected from the first phase sample. So now we have defined the double sampling ratio estimator y dr bar, that is y bar by x bar into x bar dash. This x bar dash is calculated based on the first phase sample, and y bar and x bar, these two are calculated from the second phase sample of size n. So now to find the expected value and the variances of this double sampling ratio estimator, we write y bar equal to y bar plus epsilon 1, x bar equal to x bar plus epsilon 2, and x bar dash equal to x bar plus epsilon 3, where expected value of epsilon I equal to 0, I equal to 1, 2, 3. So now our double sampling ratio estimator YDR bar for estimating the population mean can be written as this is y bar plus epsilon 1 divided by x bar plus epsilon 2 into x bar plus epsilon 3. Now this is equal to y bar equal into 1 plus epsilon 1 by y bar divided by x bar into 1 plus epsilon 2 by x bar into x bar 1 plus epsilon 3 by x bar. So this is equal to, now x bar cancels out. So we have only y bar into 1 plus epsilon 1 by y bar 1 plus epsilon 3 by x bar 1 plus epsilon 2 by x bar inverse. Now this is equal to y bar 1 plus epsilon 1 by y bar minus epsilon 3 by x bar plus epsilon 1 by y bar into epsilon 3 by x bar. This will be 1 minus epsilon 2 by x bar plus epsilon 2 square by x bar square plus up to so on. Now our double sampling ratio estimator, that will be equal to y bar 1 plus epsilon 1 by y bar minus epsilon 3 by x bar minus epsilon 2 by x bar up to first order of epsilon. Now we will neglect this epsilon square, order of epsilon square. Now this implies y dr bar minus y bar, that is equal to y bar whole into epsilon 1 by y bar minus epsilon 3 by this is plus epsilon 3 by x bar, this is a plus 3 by x bar minus epsilon 2 by x bar, neglecting this term, second order of epsilon square. So now this will be equal to epsilon 1 plus r into epsilon 3 minus r into epsilon 2. So this expectation of y dr bar minus y bar, this is equal to 0. That implies expectation of y dr bar, that is equal to y bar. So this is the double sampling ratio estimator y dr bar gives an unbiased estimate of the population mean y bar up to first order of approximation only. So we have to find the large sample variance. Large sample variance of double sampling ratio estimator. So we consider variance of y dr bar, that is equal to expectation of y dr bar minus y bar whole square, that is equal to expectation of epsilon 1 plus r epsilon 3 minus r epsilon 2 whole square, that is equal to expectation of epsilon 1 square plus r square expectation of epsilon 3 square plus r square expectation of epsilon 2 square plus 2r expectation of epsilon 1 epsilon 3 minus 2r expectation of epsilon 1 epsilon 2 minus 2r square expectation of epsilon 2 epsilon 3. So now we can see that expectation of epsilon 1 square, that is equal to expectation of small y bar minus capital Y bar whole square, that is equal to sy square by n. By neglecting finite population corrections, expectation of epsilon 2 square, that is equal to expectation of x bar minus x bar whole square, that is equal to sx square by n. Similarly, expectation of epsilon 3 square equal to expectation of x bar dash minus x bar whole square, that is equal to sx square by n dash, because this is for the first phase sample and first phase sample is of size n dash. Now expectation of epsilon 1 epsilon 2, that is equal to expectation of y bar minus y bar into x bar minus x bar, that is equal to syx by n. Expectation of epsilon 1 epsilon 3, that is equal to expectation of y bar minus y bar into x bar dash minus x bar. So that is equal to expectation of y bar minus y bar into, here we can see this x bar dash, it is based upon a sample of size n dash. So that is the first phase sample. So first phase sample, from this n dash we select the second phase sample of size n. So x bar is a part of x bar dash, because x bar dash is based upon the sample of size n dash, which is large, and the second phase sample is of size n, which is selected from these n dash units. We calculate x bar based upon the second phase sample. So x bar is a part of x bar dash. Now we can take n dash equal to n plus n1. So x bar dash, that is equal to n x bar plus n1 x1 bar divided by n dash. So this is using this in place of x bar dash, we get this is expectation of epsilon 1 epsilon 3 equal to this into, in place of x bar dash we take n x bar plus n1 x1 bar divided by n dash minus x bar. So rewriting, this will be expectation of y bar minus y bar into n x bar plus n1 x1 bar minus n dash x bar divided by n dash. So this will be expectation of y bar minus y bar n x bar plus n1 x1 bar minus n dash equal to n plus n1. x bar divided by n dash. So now this is equal to expectation of y bar minus y bar into n x bar minus x bar plus n1 x1 bar minus x bar divided by n dash. So this will be equal to n by n dash expectation of y bar minus y bar into x bar minus x bar plus n1 by n dash expectation of y bar minus y bar x1 bar minus x bar. So now we can see this is y bar minus y bar. This is based upon the n units. So n dash is consist of n and n1 units. So this basing upon this second phase sample of size n, we calculate y bar, and n1 units we have calculated x1 bar. So n and n1 units, they are two different sets. So x1 bar is calculated based upon the n1 units, y bar is calculated based upon the n units. So y bar and x1 bar, they are calculated independently here. So this term, this expectation term becomes 0, because this is based upon n units, this is based upon n1 units, and n dash equal to n plus n1. There are no units common between these two groups. So now this will be equal to n by n dash expectation of y bar minus y bar, x bar minus x bar. So this will be SYX by n. So this will be SYX by n dash. Similarly, expectation of epsilon 2, epsilon 3, that is equal to expectation of x bar minus x bar and x bar dash minus x bar. So proceeding just in the similar manner, we can get this is equal to Sx square by n dash. So now using these values, variance of the double sampling ratio estimator is now given by Sy square by n plus r square Sx square by n dash plus r square Sx square by n plus 2r Syx by n dash minus 2r Syx by n minus 2r square Sx square by n dash. Now this is equal to 1 by n Sy square plus r square Sx square minus 2r Syx plus 1 by n dash 2r Syx minus r square Sx square. Now see, the variance of the double sampling ratio estimator consists of the two terms, first term and this is the second term. The first term, it is the variance of the usual ratio estimator, and the second term, usual ratio estimator when x bar is known to us, and the second term is therefore the increase in the variance due to the use of the double sampling, where we estimate x bar by x bar dash. Thank you.